solving problems involving exponentials and logarithms. We're going to have a look at 8 different problems which involve logarithms and exponentials set in different contexts. We're going to apply the skills that we've previously learnt about using exponentials and logarithms and solving equations and simplification. So let's start with example 1. We have a population which is modelled exponentially. So remember we talked about exponential growth and exponential decay previously. So here's the equation, and we know that A and B are constants. Let's read through the information. The population is initially, which means at time t equals 0, 8 million, and it declines to 6 million after 1 year. So when t equals 1 year, the population is equal to 6 million. Use this information to calculate the values of A and B, giving B correct to 3 significant figures. So we have 2 facts that we can substitute into our equation for P. When the time is 0, the population is 8 million, so we know that 8 is equal to 5 plus AE to the power of 0 when t is 0. E to the 0 is equal to 1, so 8 equals 5 plus A, so A is equal to 3 exactly. Now, calculating B, let's substitute in this piece of information and use the fact that we know what A is as well. So this tells us that 6, which is our value of P, is equal to 5 plus A, which is 3E, to the negative B, because of course we're substituting in t equals 1. Let's rearrange this. So 1 is equal to 3e to the minus b, divide by 3. A third is equal to e to the minus b. And now we can take natural logs ln of both sides. So ln of 1/3 is equal to ln of e to the minus b, which of course is minus b. So b is equal to negative ln of 1/3. And they want us to give this correct to 3 significant figures, which is 1.0986 ... so rounded 1.10 to 3SF. Now, part 2 of this question, what is the long-term population model? Now, if we're asked to find something like the long-term information, this means that we are allowing t to approach infinity. So t to get larger and larger and larger. Now, e to the negative bt will then approach 0. Think about this. E to the negative bt is 1 over e to the bt. If you allow t to become very, very large, e to the bt will become a very large value, so 1 over the very large value will become very small. Now, if you're ever not sure, use your calculator, choose a large value of t, substitute it in and see what happens. So this part of the calculation will become 0, so that means that p will simply approach 5 million. And this is the long-term model population prediction. Example 2. The value of a car, t years after it is new, is modelled by this equation here. A and K are positive constants, which depend on the make and the model of the car. So, in the first part of the question, the model equation that we're using is this. So our A value is 20,000 and our K value is 0.2. Calculate how much value to the nearest £100 this car has lost after 1 year. So let's work this out. Part 1. So if t equals 0, we get the starting value of the car, which of course is 20,000. We can work that out easily. So after 1 year, v is equal to 20,000 e to the power of negative 0.2. Now we want to know how much value the car has lost after 1 year, so simply going to do the initial value, subtract the value after 1 year, which comes to £3,625.38. And we want to give the answer to the nearest £100, so that of course is £3,600. Part 2. So Kate buys a new hatchback for £1,500, which of course means that the A value is 1,500 because this is the value of the car when t equals 0. And her car loses £2,000 of its value in the first year. So we know that the equation for Kate is V equals 15,000 e to the negative kt. And we know that if t equals 1, we can substitute this in. So the value is equal to 15,000 e to the negative k. Now, we know the starting value of the car is this number, 15,000. And we know that this is the value after 1 year. We also know that the car loses £2,000 of its value in this first year. So we know that the difference between the starting value and the value after 1 year is going to equal £2,000. And we then need to solve this equation to find out the value of k. So I'm going to rearrange this. So I know that 15,000 e to the minus k is equal to 13,000. E to the minus k then equals 13,000 over 15,000. If we then take natural logs of both sides, we will find the value of negative k, which we can then use to find the value of k. So negative k equals the natural log of, and of course, when we do this division, all of these will cancel, so it's ln of 13 over 15, which comes to negative 0.1431, etc., which means that k is equal to 0.143 to 3 significant figures. So, part 3, find out how long it is before Brian and Kate's cars have the same values. So, just a note, the value of k that we calculated for Kate's information, I've stored in a calculator memory, so we can use the exact value of that rather than a rounded value. We're trying to find out how long it takes before the cars have depreciated to the same value, so we will set the equations equal to each other. Now I'm going to start simplifying. So effectively, this can be written as 20 over e to the 0.2t equals 15 over e to the kt. And let's collect the e terms on one side. So in fact, I'm going to write this as e to the kt over e to the 0.2t equals 15 over 20. And then we can collect the terms here and simplify our indices as e to the kt minus 0.2t. Thinking about the fact that we're dividing, the bases are the same, we can subtract indices. So this is then equal to 3/4 on the right-hand side. And we have a simple equation that we can now take logs for. So taking ln of both sides will give us kt minus 0.2t here, which equals ln of 3/4. Going to factorise t out here, k minus 0.2 equals ln of 3/4, and of course we actually know what the value of k is because we stored it in a calculator memory, so we can simply input this and rearrange to find our value of t. So input that into your calculator and see what you get. So this comes to 5.0559, etc., and we can say effectively that's 5 years or 5.1 years to two significant figures. Example 3. The temperature, theta, of water in a container is modelled by this equation. And we have three constants, A, B and K, all of which are positive. The initial and the long-term temperatures of the water are 15 degrees C and 100 degrees C respectively. Let's make sure we understand exactly what that means. So this tells us theta equals 15 when T equals 0. That's what we refer to by initial. And then over here, theta is equal to 100 degrees C as T approaches infinity. And that's what we mean by long term. We then have a third piece of information, which is after 1 minute, the temperature is 30 degrees Celsius. So that tells us that theta equals 30 degrees when T equals 1, which is just an additional piece of information. Part 1, find A, B and K, three unknowns. And of course we have three pieces of information with which to find them. I'm going to start by substituting in T equals 0 and theta equals 15, and we'll see what that gives us. So we then find out that 15 is equal to A minus B e to the power of 0. E to the power of 0 is of course 1, so this gives me 15 equals A minus B, and I can't do anything further with that for the moment. So I'm now going to substitute in the information here. What happens as T approaches infinity? So as T approaches infinity, e to the kt would also approach infinity, which means e to the negative kt would approach 0. So effectively, all of this part will become 0, and we're left with our value of A, which has to then be 100. So 100 equals A. Now this then allows us to go back to this equation here, 15 equals 100 minus B, and that allows us to work out that B is 85. So we now have the value of B and the value of A. And we then need to use our third and final piece of information to find the value of K. So this piece of information here. So we know that 30 is equal to A, which is 100, minus B, which is 85, e to the negative kt. But of course we're using t equals 1, so it's just negative k. Let's now rearrange this equation. So 85 e to the negative k equals 70. E to the negative k equals 70 over 85. Take natural logs of both sides. So negative k is equal to ln of 70 over 85. And this then allows us to work out the value of k, which is 0.194156 ... I'll round that to 3 significant figures, and we're also going to store this in a calculator memory in case we need it later on. Part 3, find out how long it takes for the temperature to reach 80 degrees C. So remember, our equation is theta equals 100 minus 85 e to the negative kt, and we now know what that value of k is. Let's allow theta to equal 80. And we simply have to solve this equation for t this time. Remember, we know what k is. So 85 e to the negative kt equals 20. E to the negative kt equals 20 over 85, dividing by 85. Take natural logs of both sides. So negative kt equals ln of 20 over 85. And then divide by negative k, which gives us a value of the time. And this gives us t equals 7.4523 ... So 7.45 minutes to 3 significant figures. Question 1 of example 4. On a single set of axes, sketch the curves of y equals e to the x minus 1 and y equals 2e to the negative x. Now you can use your graphical calculator to help with this as well, but they are very easy transformations to sketch. E to the x minus 1, first of all in red, this is a translation with a vector 0, minus 1. So we'll draw in the new asymptote, which is y equals negative 1, and the graph will look a little bit like that. So look at the y-intercept, it's moved from 0, 1 down to 0, 0. Now, the second function, 2e to the negative x, we have here a reflection in the y-axis here and a stretch in the y direction with a scale factor of 2. So the graph will look like this. Its asymptote is still the x-axis. Its y-intercept is 0, 2. Let's make a note of that y-intercept there. It's 0, 0. Right. Let's label our sketch and move on to part 2. Find the exact coordinates of the point of intersection of these curves. So the point of intersection over here, we'll call it P, is where we can equate the two equations of the curves. So e to the x minus 1 must be equal to 2e to the negative x at that point P. Let's now rearrange this equation. So e to the x minus 1 equals 2 over e to the x, rewriting the right-hand side. I'm going to multiply both sides by e to the x. So I have e to the 2x minus e to the x equals 2. And if you watch the previous video very carefully, you will realise that this is an equation that can be factorised a little bit like a quadratic. Some people like to think of it as a quadratic equation in disguise. Now, if you want to look at the comparative quadratic, you might want to think about m squared minus m minus 2 equals 0 and how you might factorise that. And of course, in this context, m is equal to e to the power of x. So, factorising this, we need e to the x and e to the x. We need a 2 and a 1, a negative and a positive. So you can see it's the same factorisation as we would have with a quadratic here. This then gives us e to the x equals 2, or from here, e to the x equals negative 1, but this has no solution. So we don't take that any further. This, however, e to the x equals 2 gives us x equals ln of 2. But remember, the question wanted us to find the exact coordinates. Now, exact means we want to leave our answer as ln2, so don't convert it to a decimal format. We do need to substitute back into one of the equations to find out the y coordinate. So I'm going to substitute into this equation here. It looks nice and simple. Y equals e to the x minus 1. So that's y equals e to the power of ln2 minus 1, which comes to 1. So the coordinates of the point of intersection are ln2 and 1. Example 5. The height, h metres, of a tree after t years is modelled by this equation here. A, b and k are positive constants. Given that the long-term height of the tree is 10.5 metres, so again, let's interpret this information. This tells us when t approaches infinity, h approaches 10.5. The initial height is 0.5 metres, so that tells us when t equals 0, h equals 0.5. We need to now find the values of a and b. So, part A, I'm going to substitute in what happens when t approaches infinity. So we know that h approaches 10.5, which must equal a minus be to the negative kt. But as we've seen before, as t approaches infinity, e to the negative kt will approach 0. So we can exclude all of this e to the negative kt part. B times 0 is 0, so this then gives us 10.5 equals our value of a. We can now use this and substitute in the second piece of information. So when t equals 0, h equals 0.5. So we can say that 0.5 is equal to a, which is 10.5, minus b e to the power of negative kt, but of course t is 0, so kt or negative kt becomes 0 as well, and we know that e to the 0 equals 1. So 0.5 equals 10.5 minus b, which simply gives us b is equal to 10. Part 2. We're told that the tree grows to a height of 6 metres in 8 years. We need to find the value of k and give our answer correct to 2 decimal places. So we know that h is equal to 6 when t is equal to 8. So let's substitute in this information. So 6 is equal to a, which is 10.5, minus b, which is 10, e to the negative kt, which is negative 8k, because t equals 8. Let's rearrange this. So 10e to the negative 8k is equal to 4.5. E to the negative 8k is 4.5 over 10. Take natural log of both sides, so negative 8k equals ln of 4.5 over 10, and we can simplify this to work out our value of k, which comes to 0.099813 ... So to 2 decimal places, that is 0.10. Example 6, we have a question involving exponential decay. So a radioactive substance can be modelled, well, its mass can be modelled by this equation here, where t is the time in years and a and k are positive constants. So part 1, an initial mass of 100 grams of the substance. So that means that m equals 100 when t equals 0, decays to 50 grams in 1,500 years. So that means that m is equal to 50 grams when t is equal to 1,500. Find a and k. So we need to substitute in the information into this equation here and see what happens. So let's start with this information. T equals 0, m equals 100, so that gives me 100 equals a, e to the negative k times t, which is 0, and of course this gives me e to the 0, which is equal to 1, so a is equal to 100. Next part, m equals 50, t equals 1,500, so I know that 50 is equal to a, which I now know is 100, e to the negative k times t, so negative 1,500k, and we can divide by 100, so 0.5 equals e to the negative 1,500k. Take natural log, so ln of 0.5 equals negative 1,500k, and from here let's work out what k is. So k is equal to a very small value, 4.620 ... times 10 to the negative 4, so 4.62 times 10 to the negative 4 to 3 significant figures. And I'm going to save that in a calculator memory, and I might save it in memory k, which means it matches the constant. So part 2 of the question. The substance becomes safe when 99% of its initial mass has decayed. That means that the mass left must be 1% of the original, which is equal to 1 gram, because the original mass was 100 grams. So m equals 1. So let's substitute that into the equation for the exponential decay. So 1 is equal to a, which is 100, multiplied by e to the negative k, which of course we now know, t. Simplify this, so 0.01 equals e to the negative kt, and ln of 0.01 equals negative kt, and then divide by negative k to get our value of t. And this gives us 9,965.78 ... So that comes to 9,966 years if we round to the nearest whole year. So, example number 7. Part 1, express 2 ln x and ln 3 as a single logarithm. So here we can use our laws of logarithms. This is ln of x squared plus ln of 3, so moving this 2 here to become the power. And then we're adding two logarithms together, so this results in a product, ln 3x squared. Part 2, hence, which means use our working in part 1, given that x satisfies this equation here, show that x is a root of the quadratic equation here. So this means we've got to use the work we've done previously, use this equation here, and rearrange to produce this quadratic equation. So let's make a start. The left-hand side we dealt with in part 1, it's the same as ln 3x squared. And this is now equal to ln of 5x plus 2, and this means that 3x squared must equal 5x plus 2, which we can simplify to 3x squared minus 5x minus 2 equals 0. So part 2, done. Part 3, solve this quadratic equation, explaining why only one root is a valid solution of the original logarithmic equation. So let's solve this quadratic equation. So I'm going to factorise it quickly, so it looks like an easy one to factorise. And this then gives us x equals -1/3 or x equals 2. But as we know, even though a quadratic might have two roots, if the quadratic was generated in a particular context, such as a practical context, we might not necessarily be able to use both roots. One of them may not be valid. And in this case, it's this root that's not valid because it's got to satisfy this equation here, and part of that equation involves us working out ln of x. Now, if we try and work out ln of -1/3, well, that's not feasible because ln of x only exists for x greater than 0. So that means ultimately we have to reject this root here, and our only true valid root is x equals 2. And so we move on to our last example here. We have the mass m kilograms of a radioactive material modelled by this equation. m0 is the initial mass, t is the time in years, and k is a constant, which measures the rate of the radioactive decay. So part 1 requires us to sketch a graph of m against t, which is interesting. We don't actually know what the value of m0 here is, so it's an unknown. So let's start our sketch. Now we know if t equals 0, and we substitute this into the equation for the radioactive decay, m is then equal to m0. So we know that the graph has a y-intercept at m0, which is the initial mass of the substance. Now, as t approaches infinity, we know that e to the negative kt will approach 0, which means that m will also approach 0. So this tells us that the t-axis, the x-axis, is an asymptote, and the graph curves down, showing our pattern of exponential decay getting closer and closer to this asymptote as time increases, but never actually intersecting it. So part 2, for carbon 14, K is equal to 0.000121. Verify that after 5,730 years, the mass m has reduced to approximately half of its initial mass. So we are going to use the formula for m. It equals m0 e to the power of negative 0.000121 multiplied by the time, 5,730. And let's input this into our calculator. And this gives us m0 multiplied by 0.4999, which is approximately half of m0. Now this word here, verify, means show. So by doing the substitution, we were able to show that the mass had approximately halved. The half-life of a radioactive material is the time taken for its mass to reduce to exactly half the initial mass. Show that in general, the half-life T is given by T equals ln 2 over K. So m equals m0 e to the negative kt. Let's replace m with half of its original mass, which is m0. So let's think about what happens if m equals a half m0. And what we're aiming to do is find out the time taken t for this to occur. Now instantly this becomes a very easy equation to solve because m0 cancels from both sides. So a half equals e to the negative kt. Take ln of both sides, natural log of both sides, ln of a half equals negative kt. And then we can rearrange this because ln of a half can be written as ln of 2 to the negative 1, which is negative ln 2. So we're using log rules here, equals negative kt. The negative cancels on both sides, and this leaves us with, in general, t, which is capital T, the time taken for the mass to halve, the half-life, which is ln 2 over k, as required. So this last part of the problem is really simple. To find the half-life of plutonium, we know the k value, we simply sub it into this result that we have found for T and work this out using our calculator. So the half-life for plutonium works out to be 24,067.610 years. So 24,068 years to the nearest whole number for a mass of plutonium to reduce to exactly half of its initial mass.